Well, we are back for another ground school. I believe this is our fourth time in the studio to do ground school. And tonight we're going to learn about weather. Woohoo! We're going to be meteorologists, people. We just don't have a blue-green screen to play. Anyway, thanks for watching, everybody. I've been getting some fun feedback at some of the local meetings on some of our videos and stuff, and I appreciate everyone that is watching and enjoying this ride along on the journey to becoming a pilot. I know the ground schools aren't the most exciting, but there will be some flying. It just happens our runway is kind of covered with white stuff, and so we can't go flying much, and we don't have skis for the planes, so we're kind of grounded until life gets better out there. So I'm looking forward to it. I did pick up a flight simulator for very inexpensive on eBay, and I've been practicing a lot on that with my turns and things I'm struggling with, and I even posted a video. If you didn't see it, check my channel, of a flight where I just flew a pattern around the Oshkosh airport and did okay on some things, but landed just a wee bit short. So anyway, thanks for watching. Make sure you like and subscribe down there to our channel to be notified as we get through this progress. Every time we post a video, every lesson, you will be notified. And just so you know, some of these videos may be shortened for length on my channel, but they will be in their entirety on Jake's channel, which is Flying Fiddler CFI, Flying Fiddler CFI YouTube, and you can see these in their entirety and learn from Jake's wealth of knowledge and information. So I believe that's, if you haven't already, you feel like helping us out with this journey, make sure you go hit our GoFundMe page up and drop a few dollars there. It will just help our budget-friendly pursuit of being a pilot, and any extra money we get just means we can fly more and rent planes and just keep on flying after we get our pilot's license. So, and that just means more videos for you to watch, because you know I'm going to have a camera there. Anyway, let's get started on aviation weather.
All right, so today we're going to be working out of a different book than we have the last three lessons. We're going to be working out of Aviation Weather, which is an FAA publication, also known as Advisory Circular 00-06B. This is sort of the FAA's Bible on weather, you might say.
It's even broke into chapters and verses.
It is goes into quite a bit of detail about weather theory, so that's what we'll be spending the next two ground school sessions talking about. Today we're going to cover hopefully about the first half of the book, and next time cover the second half if all the timing goes according to plan here. So we'll start out and talk a little bit about the origins of the weather that we experience. So in essence, all of the weather that we experience is due in some way or another to solar heating of the Earth's surface by the sun. So the sun obviously shines down on the ground and on the ocean, warms up the ground, warms up the water, but it warms up at different rates. So some areas absorb more heat, some areas absorb less heat. And the uneven heating of the ground and the uneven heating of the atmosphere then is what, in essence, in the very basic level, sets up our weather systems. So obviously the ground, hard, dry ground, will absorb more solar energy and radiate more solar energy than oceans will typically. The ocean will just dissipate that heat into a huge mass of water, and that differential in temperature causes air to warm up at different rates. As we've talked about in some of the previous ground school lessons, warmer air is less dense, cooler air is more dense, and as you get changes in air density, you start to get movement. So how does this all work? Here in Chapter 2 of Aviation Weather, we're looking at Figure 2-3 here. Just shows the solar radiation in the form of light anywhere from the top end of the electromagnetic spectrum all the way down to infrared comes off the sun, and some of it hits the Earth. Of course, infrared is the wavelength of light that carries the most heat. So as the sunlight strikes the Earth, it warms it up. The Earth absorbs that and will eventually re-radiate that back out into space as solely infrared. So it will take in all of the spectrum of light and radiate mostly in the infrared. So if you were to take a picture of the dark side of the Earth with an infrared camera, you would still be able to see the Earth there to some extent. Moving on, not only do different parts of the Earth absorb different amounts of solar radiation based on what they are, but also based on what angle the sunlight strikes it at. So near the equator, the sun is shining directly down on the surface of the Earth, and that will impart more energy to the ground, whereas if the sun is shining at an oblique angle to the ground, it'll impart less energy per square foot or square meter or whatever unit of measurement you want to use. So here in figure 2-4, we have a good illustration of this, where you have a certain amount of sunlight shining down. If it's shining straight down, that is spread over a certain amount of ground. If it's shining at an angle, that same amount of sunlight is spread over a much larger area of Earth, and so imparts less energy for each unit of area.
That's why it's warmer at the equator.
Right. So the Earth absorbed more energy at the equator. This is why it's warmer typically in the tropics. It's also why as the sun warms up the ocean, you tend to have more water vapor in the atmosphere near the equator in the tropics. So that's why you tend to have more rain in tropical climates. The sunlight warms up that water, it evaporates more. As the air gets more and more water in it, you get more clouds, more rain, and that's why the equator and the tropics tend to be warmer and wetter than, for example, we are up here in Wisconsin.
We're wetter, we just have white stuff.
Yeah. So, looking at how does the solar heating of the ground transfer to the air? Well, the sunlight doesn't heat the air directly very much. What it tends to do is it'll heat up, as we said, the ground or the ocean, and the heat radiating from the ground will then heat up the air, because air is pretty transparent. It doesn't stop or absorb much light.
It doesn't have a hard mass that can absorb the heat.
Right. It doesn't have a hard mass, and it doesn't have anything that blocks light. You know, if it's opaque, then it's absorbing some kind of light. And air, since you can basically see right through it, obviously is not absorbing very much. So what absorbs the light is the ground. The ground then radiates heat in the form of infrared, which then helps to heat up the air just above it. And they have an example here of how that works in the case of a stove. You have the heating element or the flame of a stove radiating heat into a pan. They also talk about here, if you're boiling water in a pan, you get convection currents from the steam coming up off the water. And that gets into a little bit of what we'll talk about a little bit later with circulation of air, but that is sort of a microcosm of what can happen in the Earth's atmosphere.
So the heat coming off of a boiling pot of water, when you can see the steam coming from a steam kettle, you see it move in the air, and it's creating those
sort of a vortex.
Yep,
almost.
and it's because it's moving and there's different temperatures. That's how you get little winds, right?
Exactly,
So.
precisely. And since the sunlight strikes the Earth obviously more directly at the equator, less directly as you get away from the equator, but also the Earth is tilted on its axis. So as it goes around the sun, the Earth is tilted 23.5 degrees, which means on one side of the sun you're getting more sunlight shining on the southern hemisphere. When the Earth comes around to the other side, it's still tilted that 23.5 degrees, but the sun is shining more on the northern hemisphere, and this creates seasons. So right now, about January, February kind of time here in Wisconsin, we're on the side that's tilted away from the sun. We're receiving less solar energy, and it's winter. Conversely, in the southern hemisphere, it's tilted towards the sun, and it's receiving more solar energy. So it's summer in the southern hemisphere when it's winter up here in the northern hemisphere. And that, of course, affects how much solar radiation is absorbed by each hemisphere and creates seasons. So here in figure 2-7, you have a chart also showing that places that are further away from the equator have a larger difference.
Because at the equator, you're closer to that place that stays in it all the time. That's
right. And furthermore, what they're also showing here in figure 2-7 is places that are closer to a large body of water. In this case, they're using San Francisco as an example, so the Pacific Ocean, have a more moderate temperature change than places that are surrounded by land, because as we talked about, the ocean tends to dissipate that heat energy throughout a huge, huge volume of water, whereas when the sun shines down on the land, it re-radiates it directly back into the atmosphere. So a coastal city like San Francisco will have much less temperature variation than their example is Kansas City in the middle of the country, even though they're fairly close to the same latitude. The temperature of the atmosphere also decreases with not only typically with as you move away from the equator, but also decreases as you move up in altitude. And this is because as you move up in altitude, the air pressure decreases because you have less air above you, and as the pressure decreases, the temperature also decreases. We have an equation called the ideal gas law, which maybe we can put up on screen here. It's the ideal gas law. It basically states that the temperature of a gas, in this case air, is proportional to its pressure, so that as you increase the pressure, the temperature also increases. As you decrease the pressure, the temperature also decreases. So as you go up in the atmosphere, the pressure decreases, the temperature decreases. And this, we can talk about a lapse rate being the rate at which the temperature decreases as you go up in altitude. And typically, we have something we call a standard adiabatic lapse rate. Adiabatic is a term which means if you take a parcel of air and you lift it up through the atmosphere, the pressure will decrease. That parcel of air that you took at the surface will expand because the pressure is going down. And as it expands, the temperature decreases. So adiabatic lapse rate is the amount of cooling that air will experience as its pressure decreases with altitude. So there's a standard average of this. Now, what we actually see as far as the temperature decreasing with altitude can vary a lot depending on local conditions. And sometimes the temperature can even go up with altitude. We'll talk about that later. But in general, the temperature will tend to decrease at roughly 3 degrees Celsius per 1,000 feet of altitude. So as you go up in the atmosphere, the average temperature will decrease by that much. Now, as I mentioned, things like local weather systems, even things like sun heating up the ground, causing air to rise, those can all affect what we see in the real world as an actual lapse rate. But the standard amount of cooling, or the standard lapse rate, gives us a baseline which we can use to discuss a lot of more theoretical aspects of weather. So here in figures 2-8 and 2-9, they show some different ways that the temperature can vary with altitude depending on various factors. You can have places where you go up in altitude and for a while the temperature just stays the same. They call that an isothermal layer. Iso just means the same, so isothermal is same temperature. So an isothermal layer is just a layer of air where the temperature doesn't change as you go up through it. You can also have a temperature inversion, where that's where the temperature actually goes up as you move up in altitude. And we'll talk a little bit more about what can cause each of those a little bit later. But just for now, to understand that the average lapse rate of the atmosphere is not necessarily what we'll actually measure at any given location. Now, we've talked about how different areas absorb different amounts of sunlight, different amounts of heat. And we've also talked about how as the sun heats up the ocean and any kind of water really, it'll tend to evaporate more into the atmosphere. So this gets into the water cycle, or they call it the hydrologic cycle, just a fancy term way of saying the same thing. And you might have learned about the water cycle in elementary school. Basically how the sun warms up bodies of water, the water evaporates into water vapor, that warm air rises, will typically condense into clouds. Eventually the clouds may form rain. The rain falls back down to the earth and runs back into the ocean again, and you have your complete cycle. Evaporation, water evaporates, gets lifted by warm air, water condenses into clouds, further condenses into rain, which then falls onto the surface of the earth, runs back into the ocean where it can evaporate again. Now a couple of things to talk about as we talk about evaporation of water into the air. The water vapor in the air is suspended in the air, but the air can only contain a certain amount of it. And if you get to that limit of the amount of water that air can contain, it will start condensing out in the form of clouds or water droplets or rain. But that amount of water that the air can contain depends on temperature. So warmer air can contain more water in suspension than colder air can. And you might have heard the term relative humidity. That is just a term to say how much water is in the air as a percentage of how much water the air can hold. But another term that we want to introduce here is dew point, which is the dew point temperature, as the name implies, is the temperature at which water will condense out of the air and form dew. So if you take a parcel of air, let's say the air is at 70 degrees, say, if you start cooling it down, well, at a certain point, we talked about how warm air can contain more water in it than cold air. So as you cool that air down, you'll eventually get to the point where the amount of water that the air can contain is the same or less than the amount of water that it actually does contain. And at that point, the water will have to come out of suspension in the air in the form of fog or dew, hence the name dew point. So the dew point temperature, or the dew point, is the temperature that you have to cool air to in order to force water to come out of suspension and form dew, fog, clouds, rain.
Which is why in the summer and our dew points are 70, 75 degrees, it's unbearably humid and
Right.
nobody wants to go outside.
Exactly. And at night in the summertime, as the air cools down, we might get down to low temperatures in the summertime of 65 degrees, 55 degrees even, depending on what the weather's doing. And if you have a dew point of 70, and let's say the air is 95 degrees in the heat of the summer, and it cools down to 65 degrees, the dew point is 70. Well, it can't really cool all the way to 65. It's going to actually get stopped at 70, because as that water condenses, that actually releases heat into the air and prevents it from cooling any further.
That's why humid nights are uncomfortable.
Exactly. And figures 3-2 and 3-3 showcase this graphically. You can see how the dew point versus the temperature relate to relative humidity. So in their example, if the dew point is 11 degrees and the temperature is 22 degrees, looks like they're using Celsius here, then the relative humidity is 50%. If the dew point is 11 degrees and the temperature is 15, then the relative humidity is 75%. And if the temperature and dew point are both 11 degrees, then the relative humidity is 100%. We say that the air is saturated. It has as much water as it can possibly contain at that temperature.
It's probably raining.
Or foggy, or something of that nature.
It's probably not friendly to be out in.
Yeah. So we've talked about how water evaporates into the air, but you can also have a different kind of change of state. You can have, obviously water can freeze into ice, or it can evaporate into water vapor. But you can also have, at very low temperatures, you can have water go straight from solid, being ice, straight to vapor through a process called either sublimation, if it's going from ice directly into water vapor without going through liquid in between. That's sublimation. If it's going from water vapor and going directly into solid ice form, that's called deposition. And when we see frost form in the mornings in the wintertime, that's an example of deposition. So the water vapor in the atmosphere, although there isn't very much of it in the winter, there is still some.
It's why the frost only happens at the 30s, and you get down or
Yep.
close to 30 degrees.
Yeah,
When you get down into the 20s, it's too cold to hold the water to do the thing, right?
exactly. So there's only so much water vapor that can be deposited on a surface. But as the same as when the temperature cools down in the evening in the summertime, the water vapor condenses into droplets and we get dew. In the wintertime, when it's very cold, the water vapor will, it can't condense into liquid because it's too cold, so it goes directly from vapor to solid in the form of frost, and that's deposition. So you have from liquid to vapor, evaporation, liquid into vapor, condensation, vapor into liquid. Obviously, liquid to solid is melting and freezing, and then we have sublimation and deposition. We've talked a little bit about this, but heat imbalances, chapter 4 in the aviation weather here, how we get heat imbalances. So different areas are heated up by different amounts. And also, as the as the sun shines down onto the surface, that heats up the surface of the Earth, that radiates heat in the form of infrared light. That will radiate or shine infrared. This is light. Technically, you could say it shines upward in the
Look
infrared.
at it through an infrared camera, you'll see it shining.
Exactly, from the Earth. And then it'll either go straight out into space and radiate back into space away from the Earth, or it might hit something which bounces that back down to the Earth. Clouds, so water vapor, tends to bounce infrared radiation back down towards the surface, so that's why it stays warmer on a cloudy night than it does on a clear night.
In the summer when it's cloudy, it won't cool down near about as much as on a clear night.
And winter's time, the same thing. It can also hit things like carbon dioxide, which also has a similar effect in the atmosphere. The infrared radiation will tend to reflect off of carbon dioxide back down towards, or scatter, it'll go in all directions, but it'll scatter some back down towards the Earth. Various other compounds in the atmosphere, methane, any number of other gases will cause that heat to be reflected and scattered back down towards the Earth instead of radiating out away. Figure 4-2 shows that very effectively, where clear night will tend to have a lot more heat that radiates out away from the Earth, and a cloudy night will tend to contain more heat down towards the surface. You can also have, on a smaller scale, the sun shining down in the daytime on the surface of the Earth. That'll heat up the air, and you can have a column or a bubble of rising air over something that absorbs heat, like a blacktop parking lot is a good example of that. And here in figure 4-3, you see how the sun heats up the surface of the Earth. That heats up the air just above it, and that air will tend to rise. Now, depending on how large and how strong that heating is, you'll either get a bubble, as is actually shown here in figure 4-3, which can separate from the source of the heating and just sort of drift away. You can't really see the bubble of hot air because it's air, it's transparent, but you can get bubbles of hot air coming off things like parking lots and things.
Plowed fields.
You
got all green corn out there, and you got one field that's brown. That will
exactly
grab some more heat.
So if the area that's being heated up by the sun is large enough, then you'll get sort of more, instead of a bubble of rising air, you'll get a column of rising air where the sun heats the ground heats the air rises, and then more cool air will come in from all sides to replace it. That cool air will get heated up also and rise as well, and more will come in to replace it, get heated up, and you get sort of a continuous column of rising air. We call this a thermal, where you have a column of rising air. Now, as we talked about, if you take a parcel of air, like the bubble that we just talked about, and you lift it up in the atmosphere, the pressure will go down. That parcel or that bubble of air will expand, and its temperature will tend to cool off. So you get that bubble of warm air, which rises and tends to cool. It may cool faster than the air around it, or it may cool slower, and that affects whether it will tend to only go up a certain distance and stop, or if it'll keep going further and further up. And particularly if it's conditions where that bubble or that column of rising air keeps on going further and further up, you'll get to a point where that bubble of air has expanded so much that it cools the air to its dew point, and then you'll get a cloud. So if you look on a sunny day, you'll see all the white puffy clouds all around, and what that is columns or bubbles of rising air that have risen to the point where they've hit their dew point because they've cooled down enough as they expand, and as they hit their dew point, the water vapor in the atmosphere will condense into microscopic droplets, which will create what we see as a cloud.
With-
Figure 4-8 here shows the variation in temperature over the course of a day. So you might think that the maximum temperature would happen at noon when you have the most sunlight, but actually that's not the case. You have through the night the Earth is cooling off, or the portion of it, that's on that side is cooling off. The ground is cooling off, and it'll keep cooling as long as there's no sun shining on it. So the coolest temperature actually tends to be just about sunrise.
Yep.
And then as the sun comes up, it starts warming the ground up, temperature goes up, and it'll keep going up as long as more sunlight is being shined on it. So the peak temperature is not quite as close to sunset as the minimum temperature is to sunrise, but the maximum temperature will occur usually in the late afternoon.
It's usually around 3 or 4 in the middle of summer, isn't it?
Yep. Most of us know this on an instinctual level, but some people may never
Because
have
the
thought
ground's
about
just sitting there baking with the sun hitting it. It just keeps, even though the sun's not as
Yep.
directly on it, it's like a surface. The longer you leave something on your stove, the hotter it's going to get.
Yep. So they show here how, as the amount of solar radiation varies, you have the most sunlight coming down at noon, but you keep having enough sunlight to keep it heating up more and more until about 3 or 4 o'clock in the afternoon in the middle of the summer, or maybe 1 or 2 o'clock in the afternoon in the winter, which is
like right now.
Yep. So we've talked about how the air pressure decreases as you go up in altitude. So typically, we talk about a standard air pressure, which here in this country we would typically measure as inches of mercury. So like you'd see on a barometer. So 29.92 inches of mercury in a barometer is the standard pressure at sea level. So obviously as you go up in altitude, they show in figure 5-3 here, the pressure goes down. So at Denver, for example, which is about 5,000 feet, they have a pressure of 24.92. So it is decreased by about 5 inches of mercury in about 5,000 feet. So about an inch of mercury every 1,000 feet you go up. Now, when we set our altimeters, we get an altimeter setting, which will be somewhere around 29.92, plus or minus a bit. You might hear anywhere from 28 something all the way up to maybe 31 something. But that's about the range of pressures that we see. Now, we set our altimeter to that setting, but since we're 1,000 feet above sea level here in Madison or thereabouts, you would expect that the standard pressure would actually be 28.92, right?
Somewhere in that vicinity, right?
And in fact, that is the pressure roughly that we experience.
I remember the old weather forecast, they would say the pressure is 28.92 and falling, which
Yeah.
usually means lower pressure, cold fronts coming through, kind of for the weather novices and home
Yeah.
people. I mean, they don't really do that anymore, do they? I don't think so in the
I haven't
weather.
heard them say that very much anymore, but you might hear people talk about, so when the Edmund Fitzgerald ore freighter was sunk, they talk about how bad the weather was that day,
Mhm.
and you might hear someone talk about the pressure, the air pressure, and I forget exactly what it was.
I think
but it was something
didn't
crazy.
they make a movie about that?
They might have, I'm
Yeah.
not sure, but it was crazy low pressure that
Mhm.
day, and that's part of that was an indication of that huge storm that came through.
Yeah.
So they have a chart here showing how pressure varies in millibars. So you have two different ways of measuring pressure that you'll encounter. The imperial or U.S. units way of measuring it in inches of mercury, or you can have it measured in millibars, which is essentially 1/1,000ths of a standard pressure. So 1,000 millibars is about 1 atmosphere worth of pressure. Now 29.92 inches actually equates to 1,021 millibars, which is why,
Close enough.
Why they originally said 1,000 millibars is a standard atmosphere, and later at some point decided it was going to be 1,021. Who knows? That's up to the people who determine standards of measurement, and I don't exactly know why they decided that.
You just have to deal with it.
That's what they decided. Now, something else they talk about here, which we talked about a little bit when we talked about, I think in one of the previous ground schools, as you go from high temperature to low temperature, your altimeter reading can change. And this is showing something about that here. So warm air, because it expands, take up more space, the rate of change of pressure with altitude in warm air is less because in order to be above the same amount of air, you have to travel further if the air is more spread out, versus if it's cold and the air is contracted. As you go up in altitude, you'll get above more of the air more quickly if the air is cold and compact than if it's warm
Well,
and
it makes
spread
sense.
out.
You got a little box. It's
Yeah.
this big, and then when it warms up, it becomes this big, but it's got the same number of air particles in
Right.
it.
So
They take up more.
to get
room
above that
warmer.
same number of air particles,
You
you have
gotta
to
go
go
farther.
farther. Now, because of the fact that we have different amounts of solar heating, which causes different amounts of temperature of the air, and as we talked about, warmer air is less dense, it expands more, and it also tends to rise, and cooler air tends to sink and contract. You'll have areas of higher pressure where you're getting more solar energy, and areas of higher pressure where you're getting less solar energy. And the low pressure areas are depicted on a weather chart. In this case, to figure 5-7, we show low pressure center, 2 low pressure centers near the middle of the country, and 2 high pressure centers near, one about by the Rockies and one sort of by the East Coast here. So what's happening here is the air is rising at those low pressure centers and it's sinking at the high pressure centers. So in order for the air to rise in one place and sink in another, it has to go from that one place to the other. So the air will tend to flow from a low pressure where the air rises and expands to a high pressure where it falls again and contracts. So you'll see air essentially, if you look at what the air is doing at ground level, it'll appear that air is converging in towards a low pressure system and diverging out away from a high pressure system, and that's because the low pressure system is taking air at the surface in and lifting it up, and then it spreads out again when it gets up to high altitude. And the same thing for a high pressure system, it's sort of collecting the air at high altitude and it sinks, and then it tends to spread out when it hits the ground. So you have air generally flowing at the ground level, generally flowing away from a high pressure system and towards a low pressure system.
That's how you get your east and west winds.
Essentially, yes. Now, in a perfect theoretical world with no other effects, the air would simply flow straight from the low to the high. I'm sorry, straight from the high to the low. But it doesn't tend to do that because if we look at figure 7-8 and 7-9, we see that as the air flows high pressure and towards a low pressure, it will experience some friction with the ground. So if the air is flowing from a high to a low, it'll tend to get dragged along with the surface, and that will continue to sort of bend the air over until the what's called the pressure gradient force, the force that's causing the air to want to move from the high to the low, is essentially the same as the amount of resistance that it's feeling. We call this Coriolis force, the force that tends to bend air around in a circle. Once those are in equilibrium, you tend to have wind flowing along a line of equal pressure. So instead of flowing straight from a high to a low, it'll tend to bend around and follow the lines of pressure. Now, there's a couple things going on here. We talked about how it experiences friction with the ground, which slows it down, but also since the Earth, if you cut a cross section of the Earth, looking from the top down, so from the sort of the North Pole down, the Earth is larger around at the equator than it is at the pole, obviously. So we all know that in order to travel around a larger circle, if you ever looked at a record or something, well, if anyone actually plays records anymore.
Record? What's that? Farther at the outer edge than it is at the inner.
Right. So it's far. The point at the outer edge has to travel further than a point at the inner edge. So the air that's sitting around the Earth, the air around the equator, has to travel a further distance to rotate with the Earth than the air that's near the pole, right? So if the air flows to the north from the equator towards the pole, well, now it's moving faster, even though it's moved inwards towards the center of rotation. So now that air is moving faster than the Earth, and it will tend to bend, as it flows north, it'll tend to bend around to the east, so it'll bend to the right. Mm-hmm. And as it flows south, it's going from an area where it's got a smaller radius to an area where it's got a larger radius, so then it's moving slower than the ground, and then it tends to bend also to the right, so it bends to the west. And that's why as air flows outward from a high, it'll flow outwards in all directions, but the air that flows north tends to bend around to the east, and the air that flows south bends around to the west, and you get a clockwise circulation around a high pressure system as the air is flowing outwards away from it. And then the low pressure system has the opposite happen, because as the air curves around out from a high, it turns to the right. But if it's moving inwards towards a low, so if it's moving south inwards towards a low, it'll tend to bend to the right and go west. If it's moving north inwards towards a low, it'll tend to bend also to the right and go east. So you end up with a counterclockwise rotation around a low pressure system, and this is shown in figure 7-9 here. So the combination of the air bending around because it's moving closer or further from the center of rotation of the Earth, and also experiencing friction with the ground, because if there was no friction with the ground, and you take air and you go north, well, now the air is moving faster, but if there were no friction, it would just keep moving faster, and you'd just have air going over the surface in a easterly direction. But because the air gets slowed down by the surface through friction, that's why the you don't simply have the air moving the same speed continuously as it moves from the equator towards the pole. Otherwise, we would have calm wind at the equator, and the wind would get stronger and stronger and stronger as you move towards the pole until you just had a strong wind blowing around and around and around. That does happen to some extent, but obviously we know that it's not always blowing 100 miles an hour in Canada, and it's not always calm in the Caribbean. So the reason for that is friction with the surface, keeping the air more or less moving at the same speed as the ground underneath it. Now if we continue on in chapter 5 here, there's a few more. We talked about how the warm air or cold air affects an altimeter reading. 5-15 shows that. Also 5-17 shows it in a slightly different way. So in summary of what we've talked about up through the end of chapter 5 here, we have differences in atmospheric heating, which cause vertical movement of air. Vertical movement of air causes horizontal movement of air because the air rising in one place has to move and sink in another. That would simply go straight from one to the other, except for the fact that as we flow away from the equator, the wind tends to bend around due to moving closer to the center of rotation of the Earth as viewed from the top. We call that Coriolis force that bends the wind around to the side. And of course, as we move further and further from the equator, that gets more and more pronounced. And you might think that the wind would just get stronger and stronger and stronger as you move towards the pole, but of course we know that doesn't happen. So the friction with the surface keeps the air roughly moving at the same speed as the Earth underneath it, plus or minus a little bit, which we experience as wind.
All right. Well, that's the first half of tonight's ground school. We will be covering chapter 6 through 10 next. Thanks for watching, folks. Remember, if I've cut any of this out, which I'm not sure if I will, remember you can see the full version on Jake's channel, Flying Fiddler CFI. Make sure to check that out and subscribe to his channel if you really want to do some nerdy learning and stuff. It's going to be a good source for him going down the road, which is why we're creating it for him. So thanks for watching. Remember to like and subscribe down there. Leave us a comment. We appreciate that. It helps us with our rankings and stuff. And we appreciate you coming along on the ride from RC to being a real pilot. So thanks for watching, and we will see you on the next episode.